Hello, this next submodule deals with features in your test fixture that you might find useful when you're composing more complex test fixtures than the ones we've seen to date. First of all, remind you that unlike the RTL subset of Verilog, there's no test fixture subset of Verilog. You can use any legitimate code, any code with correct syntax. There's different ways in which to apply the test vectors that you produce using the methods we discussed in the previous submodule to the design. You can do these on the fly, you can read them from an array, or you can read them from a file. So far all we've been doing them is on the fly. It's quite useful to read them from a file that's actually stored in an array inside the design. We'll talk about the different ways to specify timing in a test fixture, relative versus absolute timing. I remind you, in all our test vectors so far, we've had separate code to produce the clock from the actual test vector test inputs to the design. And I again remind you, it's very useful to compare the outputs of your design with what you expect to see and find bugs in that automatic fashion rather than inspecting the waveforms and looking for things there. So here's an example on the fly generation that also illustrates how rich the code set can be in test fixtures. Here we have a task. You might recall a task can contain timing, but not if it's being synthesized. Well, this isn't being synthesized, so it can contain timing, in particular these fixed delays. This task is actually producing a particular type of refresh cycle for dynamic memories. RAS before CAS refresh cycle, the details don't matter. What it's doing is performing a task that's quite common in this particular test fixture, and the code is simply cycling these RAS and CAS signals. So whenever you want to do a refresh in the test fixture, all you do is launch this task by calling it refresh RAS and CAS. Quite often, you want to apply a series of test fixtures to the same input, to a particular input of one design. It is very useful to store these in arrays of vectors. You might recall we saw this in the register file example. What we have here is an array of source vectors, each 16 bits wide, and we have test cycles, numbers of them. The parameter test cycles is set up the top here. We have the expected result vectors, 8 bits wide, and again we have test cycles on them. And the idea is that we over time apply the source vectors to input A in A and look at out B to see if we're getting the right result. Here I've assigned the contents of those vectors, at least the first vector, just using assignment within this particular initial block. Another initial block here that's actually applying the results to the design. I'm opening a file where I'm going to collect all my error information. Set clock equals 1. Remember the clock is cycled and always at blocks separately. Then I have a for loop that's simply iterating through my test vectors, one at a time, applying them to the input in A of the design that's attached to this test fixture. Here, one cycle later, I'm looking at the output from that design and comparing them with the expected result vector. If I get an error, I write the results to errdat.txt because that's assigned to this fopen up here. Error in loop I %d means a decimal. I is the iteration of the loop that the error occurred in. So this way, I'm checking the results to see if the correct outputs are coming out at the correct timing, and I'm going through an entire set of source vectors in order to do this. Now, rather than assign the source vectors inside the design, it is actually much more convenient to read them in from a file. And that's what I'm showing you how to do here. That's done using this $readmemh command. What this is doing is looking at the file source_vec.txt, taking the contents of that file and assigning them to the array of vectors, source vectors, one line at a time. The H in readmem H, of course, means hexadecimal. Here's an example of source_vec.text. You notice the use of comments here. Of course, those are ignored. Otherwise, we've got these 16-bit data values, which become successive elements in the array of source vectors. So source vector 0 will be assigned to 73HF, source vectors 1 will be assigned to BEEF, BEEF, and so on. This is obviously much more convenient than what I had in the previous page, where I had this initial block in which I had to write out and assign all the source vectors. It's a lot less typing. Also, it creates a very straightforward way to translate source vectors produced from your sea-level simulations to source vectors that can be read into your Verilog file. Next, I want to cover absolute versus relative timing. So far, we've been using relative timing. That is, we have a begin and an end defining the procedural block, and the delays just simply accumulate. So that at time 1, in 1 and in 2 are just set to 0, 0, 0, 1. Clock period later, clock period is assigned to 10. So at time 11, 10 plus 1, in 1 and in 2, change to 0, 1 and 0, 0. And at clock time 21, clock period plus 1, 1, 1 and 1, 0 are assigned to in 1 and in 2. The code is just simply executed from top to bottom, thus these delays accumulate. An alternative is to use fork join. In fork join, the code between the fork and the join is not executed in parallel, in series. It's executed as if it was statements in parallel. It's not synthesizable. Remember, we talked about blocking versus non-blocking assignment for a similar type of purpose in synthesizable code, but fork join is not synthesizable. So that means the delays between the fork and the join don't accumulate. All these are executed in parallel, but because they have different delays, they'll appear in the waveform at different times. In 1 and in 2, at time 1 to 0, 0, and 0, 1. At time 11, because clock period is set to 10. In 1 and in 2, we'll change to 0, 1 and 0, 0. Clock period 21, clock period times 2 plus 1. In 1 and in 2 will be set to 1, 1 and 1, 0. You might ask, what's the utility of this? I'm producing the same waveform as the previous example. The utility is if I have a very complex set of commands being applied to a design and I want to clock cycle exactly 1,121,236, apply this particular input. In begin end, in relative timing, in relative timing, I have to keep track of my total accumulated simulation time to know when I get to clock cycle 1,200,000, whatever that number was. In relative timing, all I have to do is say hash that time, set that input as part of the fork join. So it's very useful when you have strings of events that are well distributed throughout the simulation and you don't have to keep track of accumulated timing using relative timing. So that's where absolute timing is quite valuable. So putting it together, you might have a test fixture that looks like this. Again, there's no inputs, outputs to test fixtures in general, though you could imagine having a hierarchy of test fixtures. We declare our local variables. Remember, variables assigned in the procedural blocks have to be of type reg. Variables are the outputs of modules, have to be of type y. We then have our initial blocks and always blocks, and we can have many of them. We're not restricted to having just one initial block and one always block. You can have as many of them as make your code easy to read and easy to manage. We then declare all our modules that are being exercised in this design. We might have non-synthesized modules, often our memories, and then we have our synthesized modules, which often you might declare as one collective synthesized module. I'll usually call that top. Remember, these have instance types. This SRAM is instance is M1, and this top module is instance is U1. That brings us to the end of this particular submodule, relatively short one. I remind you that of the main points from this. A very good practice is to generate sets of test vectors and the expected outputs from a higher level version of your design, typically in a higher level code such as C. Use readmemh to read in those test vectors and the expected results. Use a for loop to run through the test vectors and compare the outputs of your design with the expected results and report any errors. Also introduced to you here the idea of different types of timing in a procedural block. Between begin and end, statements execute as if they executed sequentially. Between fork and join, statements are executed in parallel. And this can be useful to get to very specific timing points that might be deep within the timing simulation that you're doing. I thank you for your attention to this module. In the next submodule, we'll look at more sophisticated ways of specifying the behavior of non-synthesized components. Thank you very much.